I'll let you know when we're up. Just pretend like we're up.
Yes, okay. So if you can see me, then welcome to the live stream for Test 1 Session 2018. So we're going to be going over questions which could be similar to the ones you'll see in your MATH1231 or MATH1241 test. So we're going to be going over questions which could be... I can hear myself. Alright, so it'll be Daniel Mansfield and myself who's just starting the stream. And we'll be going over the questions that you see up here. So I'm actually going to start with this. Now, I expect most of you would have been here for MATH1131 or 1141 last session, so probably our advice about what to do in the test, well, I think some of it's worth repeating. Bear in mind that you do only have, is it 50 minutes for these tests? I think, yeah, 50 minutes for the test. Really it's 25 minutes for the calculus half and 25 minutes for the algebra half. So if you particularly click at one of them, I guess that could give you time to work on the other. But you really should aim to use no more than 25 minutes for either half. So if you get to the 25-minute mark halfway through and you're still working on calculus, it might be a good idea to stop that and start working on the algebra half. Do you want to keep those up so we can see the questions?
Oh, I was going to give us these.
Oh, we can do that too.
Hello, everybody. Cool. So yeah, we'll just put these here, so we know what the questions are as well as you. You should see them here. Yes. 50 minutes. No calculator.
No table of integrals, which is again, it's just telling you that you shouldn't expect to need a table of integrals. You will need to know some basic integrals, so you may need to know the integral of sec squared is tan, or the integral of sec times tan is sec, but you shouldn't need any fancy integrals, I don't think.
Yeah, and it's really a statement of intent and what you can expect in the test. Bring some paper, it's a good idea. Do not try and do the whole exam on that coloured sheet of paper you get given. Bring paper, use the paper, maybe even bring a stapler and a ruler if you want to.
Yeah.
Maybe ruler. Ruler on 50-50. I'd bring a ruler.
I would also bring a stapler. I mean, actually I'm not tutoring this session, but as a tutor I'd always bring one, but it was always nice if a student brought one as well.
Yeah, really stood out. Josh, would you like to go first?
Sure. Right, so this is a very typical question that you'll see. We have a set S, which is a subset of, in this case, R4, so it's a subset of a vector space. And the question asks us to prove that this is actually a subspace, so it is itself a vector space. Now, you're going to do this using the subspace theorem, and so the subspace theorem says you need three things. You need to contain the zero vector from the space above, so in this case R4, and you need to be closed under addition and scalar multiplication. So let's do the easy thing first. Let's just show that S actually contains the zero vector from R4. So the zero vector in R4 is, I'm going to actually give it a name. I'm going to call it Z is equal to 0, 0, 0, 0. So that's just a statement. This is the zero vector. And since Z1 minus 5Z3, well, in that case, that's just equal to 0 minus 5 times 0 is equal to 0, and that is the same as 2 times Z4. So I've just shown that these combinations of the elements of Z do add up to this combination of the elements of Z, which is just a fancy way of saying, well, this just shows that hence, so full stop, hence Z above is in S. So there is the zero vector from R4 in S. Okay. So next thing we have to do is show it's closed under scalar multiplication and addition. This one, I might just rub this part out because I am going to
try a different pen. I think that one needs to be retired.
Okay.
I will honourably retire it.
Yes, that's okay.
Before you do rub that out, by the way, I really like what Josh has done here. Sometimes I see tests and it says clearly zeros in S, and then they just move on, and that doesn't really give me anything to give a mark to. What Josh has done is written what 0 is, and then demonstrated that it is in fact in the space. So there's something here. I mean, it satisfies the condition. So great, this is exactly what you need to do to demonstrate that an element belongs to a set. So cool. Thank you, Josh. I just wanted to mention that.
Okay. Let's see. Okay. Now, well, let's show it's closed under addition first. So let's take. Well, I need to take two vectors from S. So I've taken two vectors from S, and I think it's important at this stage to remind ourselves what this actually means. So since these are in S, what I get is that if I take the first element of U minus 5 times the third or component of U, that is going to be equal to twice the fourth component. And likewise, we have for V, the first component of V minus 5 times the third component of V is 2 times the fourth component of V. Now, actually, I'm having a little trouble writing U and V because they're very similar to write down, so maybe pick different letters. I'll just try and be careful from here on. Alright, so I've taken these two vectors and reminded myself what that means. And now what I need to do is look at what I get when I take the sum. And I think this is much easier if you give it a name. So I'm going to let W equal to U plus V. Just as a reminder, that means W will be the vector where I just sum up so the components of W are just the sum of the components of U and V. Again, U and V, very similar characters, so maybe I should have picked different ones. That's perfectly clear. Okay, so what I want to do is I want to look at what happens when I just plug in the components of W into that condition. So consider this, and what I can see, well, I know this is going to be a reason, so since if I take W1 minus 5 times W3, well, you can see them here, these components. This is really U1 plus V1 minus 5 times U3 plus V3. Now, if I rearrange this, this will be exactly the same as the expression U1 minus 5 times the U3. So U1 minus 5 times U3, I've just moved the U's onto this side, plus V1 minus 5 times V3. And I know something special about these two combinations. It's written up here. So this first combination is 2U4. This is really 2U4. And this combination here, according to this, is 2V4. And I might just remind whoever my marker who's reading why this is true. This is since U and V are in S. Now what's nice about that is this really is just 2 times U4 plus V4, which is the fourth component here. It is the fourth component of W. Right. So I think they can see the bottom of the board, can't they? Yeah. So therefore, well, that tells me that these two vectors I pulled from S are still in S. therefore, the sum of these two is in S, i.e. closed under addition. S is closed under addition. Any comments about this?
Aside from that, I like it. It looks good. I always get comforted when I see someone who's doing this, and I can tell if it's going to be a good response just based on the first line. If they take U and V from S, I'm already happy. I think this is so important to take the elements from S, and this is really your only hope of concluding that U plus V will be in S. Otherwise, they're just vectors from R4, and there's going to be not necessarily any relation on their components. So the fact that you start with elements of S, that just makes me very happy. Of course, the rest of it is absolutely correct, but I knew it was going to be like that just by that first line. Well, I suspected.
Right. Yeah. One thing. Yeah, I still think this is important. It's not just important for me for explaining it to you. It's also, I think, important for yourself when you're writing it to realize this is all you have to start with. This is the only thing you know when you pick out these two elements. You know that these two combinations are equal, and that's it. Then you want to know something special about this combination, which you get.
There's only two pieces to the puzzle: the stuff that you know and the stuff you have to prove. So they kind of fit together naturally. Cool.
So should I do the last part of this?
You know what? I don't mind.
Okay. Well, I'll finish it off then. The next part is pretty much the same, so I don't think you're going to see anything particularly. Well, it won't be particularly impressive, but it's important to finish off the proof. So we know it has a zero vector in it. It is closed under addition. We just want to know whether it's closed under scalar multiplication. And pretty much we can just repeat the same proof format and get an answer. Alright, so pretty much the same way. Before we took two elements because we want to look at their sum. Now I'm going to, oops. I'm going to take a real number. Now, I like calling the real numbers these Greek letters, so I'm going to call one lambda. This is my field. And I need to take another vector. So again, I'm just going to take a vector, call it U, from S. So again, this is from S, so let me just remind myself, all I know about U at the moment is that U1 minus 5 U3 is equal to twice U4. And I still think it's very good to give this new construction a name. So let's consider what happens when I take a new vector. I'll give it a different name than the earlier one. What's a good vector name?
X.
X? Yeah, why not X? So let's let X be what happens when I multiply my scalar and my vector from S. So just to remind you, that would be the vector whose components are lambda U1, lambda U2, lambda U3, and lambda U4. So again, this is my reason. So since when I take the components of X and look at x1 minus 5 times x3, well, those are up here. That's this component and this component. It's lambda U1 minus 5 times lambda U3, the third component, which is just lambda times U1 minus 5 U3. And again, I recognize this. I know something special about this combination. It's actually twice U4. That's 2 times, actually, I wouldn't do it that way. That's lambda times 2 U4, or in other words, 2 times lambda u4. And lambda u4 is just this fourth component. So it is really just twice the fourth component of x. Alright, so that's the reason. So since that is true, well then I know that x is actually an element of S. It satisfies that relationship. Hence, S is closed under multiplication by scalars. Alright, so I'll just put the final reason over here. So the reason we were doing that is because if those three things are true, the subspace theorem just says, okay, that was definitely a subspace. So hence by the subspace theorem, S is a subspace of R4. And I think it is important that you do add this conclusion because the subspace theorem really does all the hard work. It checks the rest of the properties are really true. And there are 10 vector space axioms. You don't want to check them all. You just want to verify 3 and let this theorem take care of the rest. Any comments, Daniel?
I really like that. Actually, really like this. I think this is nice that you're giving a name to this, and therefore showing that this thing is an element of the set. I like that. I'm going to do that in the future. I thought that was nifty. Aside from that, you still have to show that there is find a non-zero element in the set.
Oh yes, part 2. You are correct. So yes, I actually started all of this just by showing you that there was a 0 element in there, but there's more interesting things than that. And your element that you find and my element might be different, but let's just find something which is more interesting than just the 0. So really, I think I would just do this by inspection. Look at it and pull out some numbers that will satisfy that equation. I'm going to be very tricky here because the easiest way for me to satisfy that equation is to have all those numbers being 0, but I do want something non-zero. So what's helping me here is I don't see the second element being used. So clearly 0, 1, 0, 0 is in S. And again, maybe I should give this a name to make it easier to talk about. Let's take U equal to this. So this is in S because, well, if I take U1 minus 5 times U3, that's equal to 0 minus 5 times 0. And that is the same as 2 times U4, also 2 times 0. So yeah, there's a non-zero element. And yeah, because that second thing didn't appear, I didn't have to do any hard work. I could just make the other things vanish. You could find other elements if you want, but that's what I'm going with. All right.
Cool. Are vectors linearly independent? Thank you. Alright, for my question, I get a bunch of vectors and I'm asked, are they linearly independent? And I'm going to start off with the definition of linear independence, because even if the wheels fall off completely during the course of what I'm about to do, at least I can demonstrate that I know what the definition is and hopefully get some kind of sympathy marks out of the person who's doing this. So, So the vectors are linearly independent, precisely when this equation here, which I've written with 3 variables in it, turns out to have no variables whatsoever, and it just had all those things are necessarily 0. We, of course, solve this using the only way you know how to solve systems of linear equations, which is to throw it into a matrix, an augmented matrix, and row reduce. Okay. My leading terms, you can see that it's in row echelon form, and from my taxonomy of row echelon form matrices, I know that this is an infinitely many solutions matrix. To this equation. If I know there are infinitely many solutions to this matrix, then I know there's infinitely many solutions to this, which means I know there's infinitely many solutions to this. And if there's infinitely many solutions, then there's more than just the 0 solution. 0 solution is what you would get if there's only one, if there's exclusively one solution to this system. But there's more. There's a lot more. There's infinitely many more. Hence, this is not a system. Is not a linearly independent set. Not. Not linearly independent. Josh.
So yeah, I guess I just want to. This is really, I think, the best definition of linear independence. There are other definitions you can get, such as one vector written in terms of the others, but this one is the best because you don't have to really know what's going to be wrong. You just set it up and look at the solutions and see if there's anything non-trivial.
Yeah, this one doesn't preference any one of the vectors, so yeah.
Yeah, so this is exactly what I do. Set up the equations, so then you know how to solve a set of linear equations. You put them in an augmented matrix, row reduce, and come to a conclusion based on what you're seeing. So yeah, so like Daniel said, there was a sort of a taxonomy of solutions, and this is one of the infinitely many cases.
If I was marking this, I'd give it a three mark kind of marking guidelines. 1 mark for knowing what the definition is, 1 mark for doing some kind of row reduction, at least knowing how to solve it, maybe doing at least one of the steps correctly, and then 1 mark for the kind of right interpretation based on whatever matrix you end up with here. So that way, at least someone who does mess up if you do manage to mess this up somewhere, just do what you would normally do, and you'll get most of the marks. So if I was to say mess up here, which is entirely possible, and to get a unique solutions matrix here, provided that final conclusion was right based on this, then you get that carry-on mark.
Yeah, as long as you haven't, most of the philosophy behind carry-on marks is if you haven't made the problem significantly easier with your mistake, you probably should get most of the marks just for understanding what you should be doing. Yes.
But I do agree. In some cases, especially, in some cases, the mistakes do make the question
Yes,
ridiculously easy.
If you make the question, that can happen. You can make the question a trivial question to answer. In this case, that wouldn't have happened with a mistake. It's still pretty much the same sort of question.
Cool.
Okay. Somebody was asking whether ODEs could be in this test, and I think they can't because ODEs is chapter 3 for calculus, and it only goes up to chapter 2 in the course outline.
Whatever the course outline says is correct.
Whatever the course outline says should be.
That's the law.
Correct. That's true. And somebody was asking about linear transformations, and it looks like that's next one up.
Good timing. Oh, is this me?
Yes, I think it is.
Okay. A linear transformation. That's interesting. So you have t, which maps from R2 to R3, is linear. And you're asked to, and you're given some values, and you're told to evaluate t of 1, 0. Well, the first thing you need to do is express. So this is part 1. Four, 5, 3.
People are saying they're having trouble with the volume.
Oh, but do I need to talk like this, or do I need to do?
Maybe it's a bit silent.
Let me just have a look at the camera.
Maybe turn off the gain on the camera.
Yeah. Let me do that. How about now? Is that better? I could just talk louder. Express this thing as a linear. Express this as a linear combination of those two things. That is to say, we need to solve. Solve this thing, it's lambda 1, and of course there's only one way we teach you to solve these things, and that's with an augmented matrix, which is the best way to solve these things. I might have to invoke fractions for this one. Actually, no, I never want to do fractions with this, but I want to take this away from this and I want to kill this off with this, so I might multiply this by 5 and I'll just multiply it by 5. See, I want to avoid fractions at all costs because I just can't do it. Something's gone wrong here. Okay, so here I have my unique solutions matrix. I'll just point out to you that it is in row echelon form. La-di-da. Those are my two terms. It's actually reduced row echelon form, which is my favorite form of row echelon form. And it tells me, well, this is the column for lambda 1, this is the column for lambda 2, and this row here tells me that 0 lambda 1 plus lambda 1 lambda 2, i.e. just lambda 2, is 3. So lambda 2 is 3. And this one here tells me that lambda 1 is negative 1. So let me just check that that is actually what it should be. So I just plug that stuff into here. Lambda 1 is minus 1 times 5, 3 plus 3 times 2, 1. Is negative 5 plus 6 is 1, and negative 3 plus 3 is 0. Hooray! So I have a self-that equation, negative 1 and 3. The whole purpose of this is to then apply t to this map. So t of this, this is what I want to evaluate, 1, 0. That's equal to t of plus 3 times 2, 1. Just because the fact that 1, 0 is this vector. This is going to be true for anything. But because t is linear, it preserves linear combinations in the right proportions. And so I can just write this stuff as negative 1 times t of 5, 3 plus 3 times t of 2, 1. Thank you very much. T is linear. I can tick off that assumption if you like. I use that to get from here to here. And then finally, I know what t does to this vector. T sends 5, 3 to 8. So it's negative 1 times 8 minus 1, and I know what t does to, should be 2. I know what t does to 2, 1. That sends it to 3 minus 1. And so this is equal to negative 8 plus 9, which is 1, and 1 minus 3 is minus 2. Behold, t of 1, 0. Josh, any comments on that?
Yeah, I think this is good. I guess when I had a quick look at this earlier, I was a little bit tricky myself in finding 1, 0. And then I realized I just need to get rid of this number here, and then I can sort of work with what's left over. So being very tricky, I said, okay, what happens if I take that number and take away 3 times? So this vector take away 3 times this one. And if you do that, you get, well, 5 minus 6 is minus 1, and this one's 0. That's by my design, and that's very close to an answer I could use. In fact, you can sort of see.
Yeah.
So you could do it that way as well if you wanted. For just two vectors. It's sort of there is a shortcut, but it won't always work.
If you are clever like Josh, you can do it that way. Then I won't get in your way. I'll just say go forth and use your cleverness to make the question easier for you. I'm just going to go through it the bog standard way and do it. I kind of like this because I'm Babylonian at heart, and I just want to go through the kind of mechanical process that produces the answer. But yeah, you could certainly save yourself a bit of time by doing it that way. Oh, what did I say t of 0, 1 was? I'll need that later. 1 minus
1
2.
minus 2.
Thank you. I'm going to stash that aside over here. Okay, for part 2. T is a linear map, so to find its matrix representation, all you need to do is know what T does to the standard basis. And guess what? Part A was what T did to the first standard basis vector, so all we need to do is find out what T does to the second standard basis vector. T of 0, 1. Well, I need to figure out what T does to 0, 1. Well, 0, 1, I can write that as, maybe I'll write 0, 1 is equal to 2, 1 minus 2 times 1, 0. So using a bit of cleverness like Josh would to write. I mean, you could just solve this using an augmented matrix, but this is what I want to know, and I know what T does to 2, 1, and I know by part A what T does to this thing. So T of 0, 1 is T of this mess, which, since T is linear, this is T of 2, 1 minus 2 times T of 1, 0. And T of 2, 1, that is 3 minus 1. And minus twice T of 1, 0, that is 1 minus 2, which is 3 minus 2 is 1, and minus 1 plus 4 is 3. I'll just call this thing A, where A is 1 minus 2 and 1, 3. And I might just check that. Because it's entirely possible that I've made some obscene calculation error somewhere. Check. I mean, this is only something you would do once you've been through the test and you've got 10 minutes left, hopefully, and you can go through and check your answers. Check T of 5, 3. Well, I'm claiming it should be equal to this. So 1, 1 minus 2, 3, 5, 3, which is 8. So, and negative 10 plus 9 is minus 1, which, according to my sheet of paper, is exactly what T of 5, 3 should have been. So I'm pretty confident at this stage that this is in fact the true matrix representation. But this is just for my own personal comfort and won't actually get me any more marks. Josh?
Yeah, I think it's always good. I mean, at this stage, you have on the question 2 values you should know what the matrix does. So you could just do them in your head. It's a bit of a curse if you do and you find there's something wrong, though, because then you want to go and fix it. So if you do check and find there's something wrong, I suggest leaving that till you've had a look at the other questions, because you're not going to be in the mood to try and find a mistake right now, and you're just going to be
making the same error over again.
Yes.
Yeah.
I mean, I like what was done here. Even if there was a numerical mistake here, I can clearly see that Daniel understands what he's doing. He really understood the process. So if there is a slight error, I'm going, okay, well, that's unfortunate, but I mean, you knew what you were doing. So, all right. So, shall we move on to what's next?
Calculus.
I'll go switch the slide. Okay, so we want to show that, so we have a two variable function. So here z is going to be a function of two variables defined using this particular formula. Now here they've been very explicit. Sometimes in other versions of the test the cosine is replaced with just an arbitrary differentiable function here. Here they're sort of being nice to you and just giving you cosine. I think it's actually more interesting when it is a more arbitrary function, but let's do it their way. So really it's just a question of calculating the partial derivatives and seeing whether it works. Alright, so let's see. Alright, so well the question's up there, and I might just repeat what the information was. We have that z is going to be the cosine of x plus 2y. So you're taking you're taking a one variable function and plugging in two variables inside here in this particular combination. So what do we know about the derivatives? So for example, let's just calculate the first partial derivative of this with respect to x. So that is just going to be derivative of cosine x plus 2y. Now, I mean, this should be fairly easy. When you're taking the partial derivative, you're just ignoring any variation in y. Y is not changing at all. Y is being held constant. So really you're just looking at the cosine of x plus a constant. And we know how to take the derivative of cosine. It's just minus the sine of x plus 2y. And if I want to be very precise, it's then the partial derivative of the thing inside, which is x plus 2y. Alright, now this, well again, this isn't changing. Y is being held constant. So this is really just the partial derivative of x with respect to x, which is 1. So this really is just minus the sine of x plus 2y. Let's calculate the other first derivative, first partial derivative. That is just the partial derivative with respect to y of cosine x plus 2y. And again, I don't really need to care about what's inside the cosine. It's still just going to be minus sine times x plus 2y. But chain rule tells me it will be the partial derivative with respect to y of what was inside. And now x is the one being held constant, so this will just give me, well, it'll just give me a 2 from this term here. So that is just going to be minus 2 times the sine x plus 2y. Okay, so I need to calculate some second derivative, so let's just do that. So I need to know, I don't need to know the mixed derivative, so I won't calculate it, but we just need to know the following two. Alright. So the second partial derivative of z, which is actually just the first partial derivative with respect to x of whatever it was I found over there, dz, partial dz, partial dx. So that is just the partial derivative with respect to x of this, minus the sine of x plus 2y, which is just, well, derivative of sine is cos, so it's going to be minus the cosine of x plus 2y. And again, I'm taking the derivative of what was inside by the chain rule, but that's just a 1, so I won't write it down. So we have that, and the second partial derivative with respect to y is just the first partial derivative of this thing over here, which is minus 2 times the sine of x plus 2y. And well, when I take the derivative, I'm going to get a minus 2 cos and another 2. So it is just going to be minus 4, the cosine of x plus 2y. So hence, I just plug those into that combination there, I get that the 4 times the second derivative of z with respect to x minus the first derivative, minus the second derivative of z with respect to y is just 4 times minus sine x plus 2y minus 4, well, minus 4 sine, wrong, so I'm minusing off minus 4 sine x plus 2y, and well, those two will perfectly cancel out to give me 0 as required. Alright. This might have been a little bit too pedantic with the answer. So what do you think of this? I mean, it is correct.
I was reading chat.
Oh, sorry. It is correct, but it is a little bit long-winded.
Yeah, so but that shows z satisfies the differential equation. It's fine to me. I mean,
it is correct, but I guess one thing I could do is I could actually just plug it directly into here and do the calculation once. Like do it. It might. No.
Isn't that what you're doing?
I'm thinking of sort of just writing down. It's 4 times the second derivative of this combination minus 4 times minus the second derivative of this, and then doing all the calculations.
Oh no, I like this. I mean, otherwise you just. I mean, it's really clear to me what you're doing, which, as someone who's reading it, I appreciate.
Okay.
Yeah.
Right.
I like it. I wouldn't change it.
Okay. Right. Looks like I'm up again. So we're going to do a reduction formula. Hopefully the image should be up now, but I want to draw your attention to the very last sentence. It says you are not being asked to prove. So you do not need to prove this reduction formula. It might actually be, I mean, there could even be a mistake when somebody wrote the test. So maybe you don't want to try and prove it. So it should be correct, but you don't want to prove it. We want you to just use it. So first thing I would probably do is actually, to make my life easier, give this combination a name. So we have this integral, which depends on n we'd like to do, and I don't want to write down that many symbols so many times. So I'm going to make my own life easier and say,
don't use the black, it's too soft.
Alright, let's see. So I don't want to keep writing down all these symbols, so I'm going to define the notation in to be standing in for the integral from 0 to 1 of 1 minus x squared to the power of n dx. Because, well, 2 symbols is a lot less than how many other symbols that is. And let me just remind myself, let's define this. And in this notation, we're given, this is what we're told, that in is actually equal to 2n over 2n plus 1 times in minus 1. That's not all, it also says here for n greater than or equal to 1. So as long as I have a number here which is greater than, an integer here which is greater than or equal to 1, I can always reduce it down to a smaller integer. So really what that tells me, I need to work out what's happening for naught, because if I have I1, that's expressible in terms of I naught. So I'm going to work this out first, because I need to know where my calculations stop in this case. So we can calculate that I0 is really just the integral from 0 to 1. Well, whatever this is, to the power of 0, that is going to always be a constant 1. So that's going to be the integral of that dx, which is just 1. Alright, so now I know what I0 is. So the question says I need to work out this integral when n equals 4. Right. Alright, so what do we have? So I1, according to this, is equal to, alright, let's just look at how the formula says. It says whatever number you have here, double it and add 1. So if it's 1, it's a 2 and a 3. So it's going to be 2/3 I0, or in other words, it is 2/3. What do we know about? Now I know I1, I can work out I2. So I2 is, again, I doubled it, so 2 is a 4. So I get a 4 over 5, it's always one high on the bottom. I1, which is 4/5 of 2/3. And I'll just clean that up to be 8/15. Maybe I shouldn't clean it up, but we'll see. Now that I know I2, I can work out I3, which is, according to this, 6/7 of 6/7 of I2, which is 6 over 7 times 8 over 15. I'm not going to clean that up because I want to get to the answer. My arithmetic's not so great. And because I'm not going to do any more of these, finally, I4, what I want, is actually 8 over 9 I3, or in other words, 8 over 9 times 6 over 7 times 8 over 15. So, just to make it very clear for the person who's reading this, hence the integral from 0 to 1, 1 minus x squared to the power of 4 dx is equal to this number. It's 8 times 6 times 8 over 9 times 7 times 15. And yeah, I don't think I want to clean that up. Okay. You can make it look nicer, but there's really no reward for doing that. Alright. Yeah, I do recommend introducing some notation. And please don't assume we know. Don't start using IN without actually defining it. Here I had to actually define this notation. It wasn't anywhere else defined. You have any questions, comments?
No, 105. I think, but yeah, you're right. I mean, if you could just leave it like that, that's probably fine.
Yeah, no, it's definitely a power of 2 on top, because I can get rid of multiple of 3 on the bottom.
Yeah, and 40, no, that's 45. 45 times 7, damn. Yeah, maybe it's better just to leave it like that.
Yeah.
But now I have to do it though. No, let's not do that. Good idea. Leave it like that. No calculators allowed, which means you can leave it like that. Next question.
Yep.
This is you again?
Yeah, so it is.
Really? I guess so. Okay.
Yep. Right.
I'll change it over.
I'll clean the board. So this one shouldn't be, again, this one shouldn't be too hard. This one should be, I think, almost one line. So we're given a 2-variable function defined, we're given a 1-variable function. No, let me repeat that. So z is a single variable, which is defined as a combination of two variables, and those variables themselves depend on one variable. So we want to find a particular derivative. Now, the following diagram I'm going to draw is not necessary. In fact, I think some people I know don't like them, but I still think it's nice to sort of get clear in your head what's going on. So, z here depends on two variables, depends on x and y, and those each depend on t, just on t. So in the end, z only depends on t. That's the only free sort of thing that you can sort of play around with. And I think there's a typo here. Yes, there is a typo here. It should say dz dt, because dx dt is too trivial. So yeah, there's a typo. This should really say calculate dz dt. So that's what I'm going to do.
Do you want to write calculate dz dt just kind of down below a little bit?
Yeah. Yeah, calculating, well, with the xdt, it makes sense, but it's not very interesting. Okay, so we want to calculate this quantity here. And it really is a full derivative just because z only depends on one variable. So it only depends on this one variable t. Okay, so it says use a chain rule. Well, the chain rule is here. We have that we're trying to calculate dz dt, and really z depends on two variables. So it firstly depends on x. There's a partial derivative with respect to x times the derivative, and this is just a full derivative, a normal derivative with respect to t. So that's one of the terms, and the other term is the partial derivative with respect to its other. So z depends on two variables, so its other variable is y times, again, y depends on one variable. So this is the chain rule you will need to use to find dz dt. Okay, so here it's just a question of doing calculations. So just, let's see, looking the partial derivative of z with respect to x is just 4 times x. And I'm timesing that by the partial derivative of x with respect to t, which is a 2t. Then I add on partial derivative of z with respect to y is 2 times y, times the partial derivative of y with respect to t, which is 12t squared. It does say make sure it is a function of t, so I should go back and replace these y's with what they really mean in terms of t, x and y. So this is 4 times t squared times 2t plus, so 2y was, let's see, that's 8t cubed times 12t squared. So all in all, I have 8t cubed plus, and again, 12 times 8, that's an 80 and another 16, so it's 96t to the 5. Right. I could leave it like this, but it's not too hard to clean it up to this. Right. So one thing I want to point out is it does say use a chain rule. So this is really the part I'm looking for if I'm sort of, we're testing you on whether you can do this part. And also you do need to get it in terms of t. If you were just to rewrite z as a function of t, then it's just taking the derivative of a polynomial, and it's not an interesting thing to do. I really want to see this bit happening. All right. Any comments or?
No, just what you said is what I wanted to say. It's also in the chat, so.
Yeah, you do need to use a chain rule. It says use a chain rule. You better use a chain rule. Right. I think...
The last question.
Yes, okay.
Okay. So we'll be just over an hour. Okay, I'm going to do this question twice. That's how much I like it. Mostly, well, not really. I'm going to do it twice because I'm going to do it the first time with just using the formula for all those people who are really perhaps don't have a lot of time to fully understand what's going on with this question. Just want the formula, just want the marks. Sure, you got it. This is what you do. Difference Z is dz. Evaluated at 9,1 times delta x plus dz dy. Evaluated at 9,1 delta y. dz. This thing dz dx evaluated 9,1, well, that's whatever the derivative of this with respect to x is, with partial derivative of z with respect to x, which is 1 on 1 plus y times 1/2 root x, evaluated at 9,1. This notation, by the way, big bar with a little subscript 9,1 means plug 9,1 into this formula, which gives me half, 2 and 3, so that's 1 on 12. dz dy. dz dy, that thing is root x plus 1 times negative 1 over y plus 1 squared, evaluated at 9,1, which is 4 times negative 1 divided by 4, which is minus 1. Okay, so I know what that is, and I know what that is. So delta z is 1/12 delta x minus delta y. And then you get given that the difference between the measured value of x and the actual value of x, and the difference between the measured value of y and you get given this thing and this thing, but in absolute terms. So delta x is 0. I'll just write as 3 over 100. Delta y, the absolute value of delta y, because it says the absolute value is at most this thing, is less than or equal to. So, well, you need to get absolute values in here, and the way you do that is with the triangle inequality. This thing is less than or equal to 1 on, well, delta x plus negative 1 times delta y, which is 1/12 times 3 over 100 plus, so this absolute value of negative y becomes just the upper bound on that. Maybe I'll write this as 1/12 delta x plus delta absolute value delta y, which is equal to this thing, which is less than or equal to this thing, because this is strictly less than or equal to 3/100ths, and this is also less than or equal to 3/100ths. So I get, what do I get? 15 over 1200, which is 5 over 400, or 1 over 80. 1 over 80. So that's what you have to do. The key parts of it are remembering this formula and knowing that you're actually given the difference between the real value of x and the measured value of x as an absolute value. So when you're making your little measurements, you're making your measurements. There's an error in your measurement, which is at most that, and similarly over here. And then knowing how to get that information into your total differential equation, a total differential approximation by the triangle inequality. Josh.
Yeah. This is, I think, exactly what I would do. It is important you use the triangle inequality because you don't really know how these terms are interacting. You don't know if this is going up, if this is going down. If you don't use the triangle inequality, you can't really come to any conclusion because there's just not enough information. Here now, it's just one thing. I'm saying, what do I know about this one thing? I know this. What do I know about this one thing? I know this. There's no need to look at any interaction.
Yeah, you don't always get given this stuff as an absolute value, by the way. In some questions, you get told that this is genuinely 3 over 100 and that this is genuinely like 2 over 100, and then you don't need to use the absolute values, and so this negative would survive. So
yes.
Just be aware that not all of the stories involving the total differential equation require you to use the triangle inequality. You need to know if you're being given, but if you have the absolute values, then you probably do need to use it.
Yeah, if I knew what these things were doing, then I could work with them together. Here I say, I only know what they're doing sort of separately. I need to somehow break it up.
Yeah.
So you said you want to do this one again?
Yeah, I want to do it again.
Okay.
I mean, this is good, and when you're doing it in the exam, then this is probably what you should do, but I want to do it maybe a bit of an algebraic method. And maybe this will, I mean, even if you do that in the exam, and I encourage you to, maybe things will make a bit more sense to you when you see it in the algebraic method, or with the algebraic method. So what you've got here is a curve. I'm going to call it let this is a curve. It defines a curve in three-dimensional space. Normal to the curve is, well, curves, this might seem a funny way to write it, but the nice thing about it is the normal to the curve is really elegant. It's just that. And so when you're writing this out, which is equal to, well, pretty much the partial derivatives we had before, 1 on, which is equal to y plus 1. Negative 1. And which is equal to, shall we say, what was it again? Which is negative 1 on 12, negative 1 at x equals 9, y equals 3, and then y equals 1. So here's a curve, The normal is given to you by this equation, and here it is, and here it is at this particular point. So what is this thing all about? You've got some crazy curve like this. You're interested what happens here at the point, shall we call it A, where x is equal to 9, y is equal to 1, and z is equal to 3 divided by 4 divided by 2, which is 2. Is that right? Yeah. And so you know this point lies on the curve. What you're asked to do is find how different this point is from another point which is nearby. So what if this value is truly not actually 9, but say maybe 9 but shifted a little bit? How bad is 2 as your approximation? So what if you're what is the difference in the z value between 2, which is what you calculated as, and some point which is nearby? And the whole idea is use the tangent plane. Forget about the curve. Curve's too hard. Use the tangent plane. Of course, the tangent at A is the normal at A. X minus 9, y minus 1, z minus 2, dotted with the normal, which gives you so here's the tangent plane in point normal form, or if I take that and move it over to one side, I get z minus 1 is equal to 1/12 x minus 9 minus 1 times y minus 1. And this, I mean, once you've set it up like this, this is what it means. This is what the total differential approximation means. Here it's d dz. Here, I'll just do it in red. This is d f dz evaluated at the point d change in x plus df dy changing y. This is, I mean, the total differential approximation is really just talking about the tangent plane to this thing, and the whole idea of using it is that the tangent plane is actually quite close to the curve at that point, and so instead of finding what the curve does at that point, you just say, well, it's approximately what the tangent plane does at that point, and so this whole thing is really just an algebraic operation. Yeah, and the story just continues from there. Anyway, that's probably not what you would do in the exam, but I think it makes a lot more sense if you think about this thing as just being a curve and the tangent to the curve, the tangent plane to the curve given to you with the normal sticking up there. Let's leave it at that.
Yeah. Maybe just one thing, if you were to try and do this, one thing whenever you write vectors as rows, I do like.
Oh, with the transpose? Yeah.
Because I always think of vectors as column vectors. So I always think writing it as a row is very convenient, but I really want it to be a column. So this is just saying that it's a space-saving thing.
Nice.
Also, you kept saying curve. Would you call it a curve or a surface?
Surface. Yeah, surface is better.
Okay. But yeah, in fact, usually I would get this. I mean, this is a very lovely formula. I think you can find, if you go through the calculus notes, there'll be a small explanation of this. I don't think we actually talked about it this way in the lectures. So in the lectures we tend not to talk too much about this particular point of view, but it is a very lovely point of view. I mean, I really like this formula. It's again, one of these very nice symmetric type setups you look at where x, y, and z, they all appear the same way in the formula. So it is a very lovely formula, and you should, computationally, I think you should try and remember that one. It's very helpful.
Yeah, but this whole total differential approximation thing, this is really just saying the curve is close to the tangent plane at that point. So if you move x a little bit, like by 0.003 centimeters, then you can use this, and that's pretty much what the curve would have given you anyway.
Yes.
Call it a day, or you got
yes.
something?
No, I was just going to say, we had to only pick out a few problems to do to make this go for a reasonable time. So there are a lot more problems in the past tests and to look at. Do remember there is still consultation hours. Your test shouldn't be until Wednesday afternoon at the earliest, depending on when your actual test is. So try and make use of the Maths drop-in centre. Try and make use of the consultation times. Especially try and make use of the Moodle forum to get some discussion. If you think you have a solution and you're not sure of it, how it sounds, you could maybe run just post it up on the forum and see what kind of comments you get. So yeah. Well, anyway, good luck with your test, and
we'll see you in lectures.
Yeah, see you in lectures.